My name's Tammy from McGill University, and I'll be chairing this session. Our first speaker is Roman Lutchyn from Microsoft, and he's going to talk about topological superconductivity in superconductor-semiconductor heterostructures. So Roman, the floor is yours.
Well, thank you, Tammy. Thanks, organizers, for inviting me to give this talk. Okay, so this is the agenda for my talk. I want to cover several topics today. In particular, there was a lot of discussion about Majorana zero modes and how we can we identify them in condensed matter systems. And so I would like to show a protocol that we developed at Microsoft, which is based on 3-terminal nanowire transport. And then I want to talk about new proposal to realize Majoranas in full shell nanowires, and finally conclude with some ideas about topological quantum computing. So probably this is well known to most people on this call. Topological phases can be either intrinsic or engineered, and there's a lot of interest in engineered materials because there's just very difficult to find materials with intrinsic origin. And we discussed today atomic chains, some TI-based proposals. I'm going to focus on semiconducting heterostructures. This is the idea that goes back to 2010, that if you take a nanowire, put this nanowire in proximity with S-wave superconductor, apply magnetic field in the right direction, and if this nanowire has spin-orbit coupling, then we showed that within this model one can drive the system into topological regime, which happens when one tunes chemical potential in the gap. Do you see my cursor? Yeah. Okay. Great. So what's needed, and this proposal can be related to the previous work by Alexei Kitaev and others, where they've shown that if you realize spinless P-wave superconductivity, then such systems will generically host Majorana zero energy states. So in order to realize this proposal, we need to have large spin-orbit coupling, have large G factor, and make sure that we have large induced gap. That's kind of basic requirements, staples, in order to realize this proposal. The phase diagram is the following. So if you start at zero field, so this is Zeeman, this is chemical potential, one starts in trivial phase, but then as we apply magnetic field and open up the Zeeman gap, at some point one can drive the system into topological phase, and these two phases will be distinct because they will have either have or not have generically zero energy Majorana states at the opposite ends of the wire. So that's the basic idea. Soon after these proposals, we seen some first attempts to realize this model in indium antimonide titanium nitride wires. So this is well-known Morik et al. Experiment, where indeed you see the appearance of zero energy state at finite magnetic field, which is consistent with the model. This is calculation for the model. But you see a lot of other things like soft gap at zero field, and it was clear, soon after this experiment, that material improvements are needed, and actually material improvements are driving the quality of devices even up today. So in order to make sure that we realize, a clean system and we have good interface, one needs to make these interfaces between semiconductor and superconductor very pristine. And here's work from Peter Krogstrup and collaborators, where they realized epitaxial interfaces, which indeed improve the quality of interfaces significantly. Later on, similar high quality interfaces were realized with indium timonite, aluminum, and the point that I wanted to illustrate here, that interface physics is very important. So this is comparison between epitaxial interface at zero field and evaporated sort of metal deposition, and you can see clear difference that in terms of sharpness of the signal, the epitaxial interface looks very similar to BCS, density of state, up to this noise floor, whereas the evaporated does not, and as we understand now, that that is due to the disorder, interfacial disorder. So previous experiments, I would say up to maybe the last couple of years, they were focusing on aluminum. Superconductor aluminum is superconductor that is relatively easy to work with, but has low TC. So TC is below 2 Kelvin generally, and that limits the size of topological gap that one can potentially realize in this system. However, very recently we've seen other interesting material combinations, being realized in the lab, and tin, indium and timonite nanowires, or lead, indium arsenide nanowires. So these alternate superconductors, they have very interesting features, much larger induced gap of the order of, MeV. And also what's nice, that they show 2E periodicity at zero magnetic field, which is, very important for quantum computation, because that tells us that we don't have quasi-particle poisoning in these devices. That's sort of material development in the field. In addition to material development, we also have been pushing theoretical understanding and even, simulation of these devices, and kind of understood the basic physics that is very obscured in the original model, because the original model is one-dimensional, it's a single channel, and so on. And one assumes that we tune chemical potential, whereas in reality, which is shown here, we don't tune chemical potential directly. Yeah, we have gates and we tune gate voltages. And actually, these gate voltages, they do a couple of things. They change the position of the band, but they also change the coupling to a superconductor. So it's important to understand the phase diagram, first of all, in terms of the measurable and controllable quantities rather than abstract quantities. But another thing that is, I think, important is that single band regime is difficult to realize in systems, and one often has to sort of live with several subbands and so on. So the reason this happens is because when you have, for example, indium arsenide and aluminum, we have accumulation at the interface. This has been shown in ARPAS studies in the reference below. And this accumulation actually is band offset, so-called band offset, is of the order of a few hundred MeV, so it's significant. And we need to take that into account. So, in 2018 and 19, we managed to produce the phase diagram in terms of gate voltages and magnetic fields. And what is interesting that, the width and the position of these different bands, they depend on the gate voltage. And essentially gate voltage in this picture changes the position of this point. And it's important consideration because it tells you which fields one should expect to get into topological field, and it alleviates another, kind of highlights another point, that there is a renormalization in these interfacial Hamiltonians. And this renormalization comes because wave function spends some time, electron wave functions has some weight in superconductor and semiconductor. So that's essentially the origin for this renormalization. So we can make some predictions, and if you have these, new superconductors, and if you can engineer this band offset at the interface, you can make some predictions as to the maximum size of topological gap. And you can see clearly the advantage between aluminum-based materials, where a peak is at most, 80 micro EV, whereas in lead nanowires, you have about 200 topo gap, and this difference is huge because the ratio of gap to temperature is in the exponent. So so that's the status of simulations, and I'm gonna show more results later in my talk. But I think we with the help of these simulations, we now understand much more about these systems. Okay, so this is sort of very important question that was discussed in the previous sessions. I don't want to, dwell on this too much, but I just want to say that local conductance is not sufficient to identify topological phase. Our knowledge evolved, and we now understand that in realistic situations with disorder and realistic disorder and all sorts of potential deformations that are present in devices, it's very easy to confuse true Majorana with some kind of accidental, or protected Majorana with some kind of accidental state. So our approach is to sort of move away from just local measurements, but really go to the heart of the topological phases of matter, which basically rely essentially on non-locality, on robustness with respect to local perturbations. So combining local physics and non-local physics is something that will give us much higher confidence that we detect true topological phase. So what is the proposal? I mean, there are several ideas in the literature. This is one of the ideas where one use, instead of two-terminal device, a three-terminal device where this superconductor is grounded. And this grounding of superconductor gives the possibility to measure local physics, so essentially map out local density of states at both ends of the wire, but also measure transports through the entire device from left to right. And one of the key features of topological phases is that transition from trivial to topological phase is accompanied by quantum phase transition that has a closing of the gap. And so correlating information, in local spectroscopy on both ends, and this closing of the gap is key to this idea and this proposal, which takes away measurement bias, confirmation bias, and gives you a procedure which tells you yes or no whether you detected the phase or not. I mean, it's not that simple as I explained, but it definitely takes away confirmation bias and selection bias. So you can see the results here, and there's a simulation results here. If you look at local conductance in this particular data set, there are lots of states. Some of them are closing, and then they move around. Some of them stick to zero for extended period period in magnetic field. But if you actually look at non-local conductance, it's pretty clear that this is a transition point. Gap is closing here, then it's reopening. So in this specific picture, Majorana would appear in this regime, and it gives you, a very clear picture, and the fact that local physics does not enter necessarily in, if the device is long enough into non-local transport is important ingredient here. So, so this is the protocol that we put forward recently, and again, the idea is that we can use data analysis routines that allow for automated and unbiased execution of this protocol, and gives you opportunity to screen out false positives that we discussed in the previous session. So let's see how it works. So here is a simulation with disorder. I mean, it's essential to include disorder in these simulations. These days, I would say, our main obstacle towards realizing topological phases is disorder. So, it's important to include these effects. So here's the device. There are different barriers on the left and on the right of the device. So the length of the device is about 2 to 3 microns. And here is the localization length. Normal state localization length is a function of field and chemical potential. So if I look in the right regime, and this is sort of the result of this topological gap protocol extraction procedure, which basically maps the phase diagram into different phases. So this color represents a region where there is no zero bias peak at both ends. This is this region where you have zero bias peak at one of the ends of the wire, and the dark red color is when you have zero bias peaks at both ends of the wire. The black line here is basically scattering invariant. So the change of the sign of the scattering invariant tells you where the phase transition should occur. And the second panel gives you non-local conductance, and this white color basically indicates where the gap is closing. So in this plot, I have 3 different lines. So let me start with the red solid line and explain this first. So this is the regime, the topological regime. We numerically checked that the localization length is longer than topological coherence length. So that's good. That means, disorder is not suppressing topological phase in, for this value of chemical potential. And you see appearance of zero energy states in both ends of the wires, as well as gap closing and reopening, basically. So that's a good regime, and the protocol identified this good regime. But now let's consider the other 2 regimes. So in this lower regime, you can see that the visibility for the phase transition is dropping. And the reason for that is that, localization length becomes very, very short, and eventually becomes shorter than even the topological coherence length. So in this regime, we don't expect to see topological phase based on our understanding of disordered superconducting phases. And indeed, if we look at local and non-local simulation, the non-local signal does not show anything, which means that in these devices, localization length is too long, and we don't see any features. But we do see zero energy states, and so if one naively measures zero bias peak only, one can see the zero energy state, and that would be a false positive. So the second line is over here. In this regime, we also are not in topological phase, but one starts to see some signal because localization length is increasing. And you know, you can clearly see in this regime that gap is closing, but doesn't reopen. So that means, you know, basically we don't see topological phase. But again, there are zero energy states in local conductance. And the combination of these two, again, allows us to identify that these regions are trivial. So that's in a nutshell the proposal. And I think, you know, we believe that sort of it moves the field forward in the sense that we care about local properties, and you know, in this experiment we are measuring directly non-local properties, and that's the direction that I think will improve our confidence that we realize topological phase. Okay, so maybe changing gears now, and I want to present another work from these co-authors of mine, led by Solar and Georg. And this is about flux-induced topological superconductivity in full shell wires. So the interesting observation, experimental observation, is that if you take the LS wire and you know, couple and just coat this wire with superconductor and then measure local spectroscopy, one sees something very different than what we used to see from just the hollow cylinders and little Parkes effect. And that is that when, you know, magnetic field is zero or close to zero, or we are in the first lobe, so no winding of the superconducting phase around the cylinder, you know, density of states looks similar to what you expect from little Parkes effect. But if we increase now magnetic field so that the winding of the phase is equal to 1, we start to see drastic differences, and this difference is that you see something that appears at you know, zero bias. And so the main question is, okay, is it something accidental, you know, something that depends on disorder, or do we have reason to believe that one can realize topological physics here? So this is the question that we set out to answer. And the key ingredients in our model are the following. So first of all, these superconductors are very thin. They are of the order of 20 to 30 nanometers, and disordered London penetration depth is about above 100 nanometers. So, you know, here the screening effects and screening currents can be neglected. It's very thin cylinder. Second, we assume that there is this accumulation layer at the interface. As I've shown before, we know from ARPA study that there's a accumulation layer with band offset of the order of hundreds MeVs. And this band offset and this electrical field, kind of radioelectrical field, is an important ingredient of this proposal. And what is important is this radioelectric field does not average out if you know, this effect of radioelectric field does not average out, despite what one would naively think, and I can explain why. And finally, we don't think for this proposal Zeeman physics is important. The main ingredient is actually orbital physics and basically angular momentum states that appear inside of this cylinder. So if you know, rewrite that model in cylindrical coordinates, one will get this, you know, very long Hamiltonian. But the important point that I want to emphasize here is that there is additional symmetry which allows one to simplify this Hamiltonian, and actually gives you a clue whether we can realize topological phases or not. So this symmetry is this generalized angular momentum operator, which is a combination of angular momentum, spin, and also this Nambu momentum, which depends on the winding or around the winding of the superconducting phase. This generalized angular momentum operator commutes with Hamiltonians, so it's a good quantum number, and therefore, in this ideal cylindrical geometry, we can label all these states in terms of MJs and identify odd and even sectors. And what is important is to also understand how particle-Hall symmetry acts on eigenstates. And so particle-Hall symmetry takes states with energy E and mj to states of minus E and minus mj. And so immediately we can see that mj equal to 0 sector is special, just like we saw something similar in vortices and so on. And so we can project the above Hamiltonian to this mj equal to 0 sector. And by doing so, we arrive at actually this model here. So this model, if you look at it, it actually looks very similar to the original semiconductor nanowire model that I described at the beginning of this talk. It has the same sort of ingredients and parameters, except these parameters now depend on geometrical effects, the radius of the wire, and spin orbit coupling and other things. So they are just related in a different way to the physical parameters of the wire. But because it's the same universality class, we immediately can say that yes, this model supports topological phases, and it has the same transition, class D, and so on and so forth. So that's great. So that means, this zero energy state that we see could potentially be of this topological origin, but we need to do more work. So that's where the simulations come in, and here it's important to take into account hexagonal geometry. It's important to take into account the thicknesses and dimensions. It's important to take into account presence of many bands and coupling and so on. And we did all of that in this model. This is what we find. So two parameters that we don't know, and that's why we chose to show them on the axis, is really what exactly is band offset. Roughly the range, but in these wires, things depend maybe on interfaces and specific material deposition. So that's band offset, and also spin orbit coupling. And you can see phase space, which has trivial and topological phases, and so whether you are in topological phase or trivial phase really depends on the geometry of the device and radius of the wire. And that's the downside of this the system, that we cannot tune chemical potential like we could before. Tunability is limited, but the upside is that the wire is covered by the superconductor, so we're not sensitive to charge disorder in the environment as much as in the other proposals. And so when we do the simulations for reasonable physical parameters, and this is the point that we've chosen for simulations, we see this picture. So this is middle of the wire. Clearly it's a gap phase, and this local density of state. At the end of the wire, you see, zero energy state, and you see some other trivial states that appear at the ends, but also, the induced gap. So I think this picture is pretty clear, and just to contrast, this is what we see in the experiment. So that's good news, because I think qualitatively we see similar results. And so the next step is to, really try to answer the question, what's the scaling of these, of the splitting between these two zero energy states as a function of the length of the wire. I think I'm going to skip this part and just go straight to the to experimental system. So bottom line is that the scaling with the system lengths should be observed in Coulomb blockaded experiments. So maybe just here, if you consider now floating superconductor, in these Coulomb blockaded experiments, one would see the shift of these even and odd parabolas, which will be dependent on the hybridization energy between Majorana states, because they will also highlight even in odd sectors. So this system, these full shell wires, actually pretty nice system for that, because we can just take one long wire and etch just different, etch different regions and make sure that we have different lengths of devices, and then start investigating how the splitting of this even and odd state, and this is a splitting between even and odd, depends on the length of the wire. So the wire was nominally the same. It's the same grown wire coated with a superconductor. All experimentalists did is just define different lengths of these wires and define gates and try to measure conductance to different sections. And this is what they find. They find that if you, at the end of the day, collapse, all the data points in this plot, that things look similar to the exponential plot, and they extracted this coherence length, which actually is pretty close to what we expect from simulations, theoretical simulations. So that's a good sign. We tried to do our due diligence and come up with some other scenarios, how Andreev states would change the splitting energy, how other states would affect the splitting energy. And it's difficult to reconcile with this plot, but I think this is the first work on this topic. And, I would just leave it here that we see, results that are consistent with the explanation, but we need to investigate the system more. So that brings me to the end of this section. And if I have maybe 1 minute I wanted to conclude. Tell me how I'm doing on time.
Yeah, you can take 1 2 more minutes.
Yeah, so where are we going with this? I mean, we're going with this to trying to realize topological protected qubits and try to encode information in these topologically protected states that would decouple from local operations. So that's the basic idea that is due to Alexei Kitaev. And so there are several sort of proposals, but I will focus on these Coulomb-based proposals. And so, fundamental question that I can ask, okay, so if I have a floating device, then, charge in this device is fixed, so I reduce ground state degeneracy. If I had just 2 Majoranas, then, there's no degeneracy because I have a global constraint. But now, if I have 4 Majoranas, and they're separated from each other, and I have global constraint, then essentially that represents a 2-level system, a degenerate 2-level system, if the lengths of these devices, the length between Majoranas is large enough. However, that introduces also phase fluctuations. And so in this paper, we studied how things depend on phase fluctuations, whether one can still define ground state degeneracy and the same physics beyond, in the regime that kind of goes beyond mean field theories. And so the answer is yes, one can still define this ground state degeneracy, although the splitting may depend on details and may become a power law rather than just exponential. Although this power law may have a very large power. So So that's one result. And later on, we, actually Plug and collaborators, and also Karzik and collaborators, we've defined how to operate these, how to control this degeneracy and how to do projective measurements. And so that's another key step. So it was shown in these two papers that one can use quantum dot to do the readout of Majorana parity at one of the end of the wire. And this quantum dot essentially projects to a certain state. And if we do these projections for gamma 1, gamma 2, and then say gamma 2 and gamma 3, gamma 4 shown here, and gamma 2 and gamma 4, they do not commute, and that's a way of introducing non-commuting operations, and that's a way to do quantum computation. So that's how the scalable design idea came to fruition. And the basic ingredient here is that we are not using the conventional sort of pulse qubit control, but rather measurement-based operations which project to different state, to different ground state, and these non-commuting operations allow one to do quantum computation, provided we have dense enough set. In Ising systems, we need to supplement with some additional operations, but I'm gonna just refer you guys to this paper because I don't think I have time to cover. But what's good about this design is the charging energy protects qubit from external quasi-particle errors. And that's good because mostly quasi-particles are generated in the leads, in superconducting leads. And so this allows one to significantly suppress quasi-particle effect in superconductors. And also it allows for electrostatic control of Majorana couplings, which, it's quite an advantage because electrostatic control can be done locally, as opposed to magnetic control, which is, very non-local. And so that's the idea, how that we will create these networks of these qubits, topological qubits, and then have quantum dots. And then by turning on and off these couplings, one can do the measurements, one can entangle qubits, and so on and so forth. And that's how one can realize this network experimentally using this nanowire networks. So with this, I will conclude and take questions.
Thank you very much for this interesting talk, Roman. We already have a question from Ali. Do you want to ask it? It comes with a paper that he wants you to comment on.
Hi, Roman. Nice to see you. Nice talk.
Hi.
So I've been, there is this paper that says these are Andreev state in this core shell nanowire experiment. Could you comment on it? And I'm not an expert on the different interpretation.
Which paper are you referring to?
It's the paper, it's on topological zero bias speaking full shell nanowire induced by flux tunable Andreev states by Marco Valentini et al.
So I put it in the chat, but maybe we can also discuss this in the discussion after this talk.
Oh,
yeah.
Sorry, guys, I just wanted to say that tomorrow my talk will be devoted to that in part.
Okay.
Great. So, maybe we can come back to that question, Ali, after that talk. I just will answer a question briefly. The jury is still kind of out. It's good that some other experimental groups trying to reproduce and do these experiments. And of course, things depend on details. As I alluded to, things depends on the radius of the wire. So, we have to have a detailed discussion and then look at the thickness of superconductor, thickness of the wire, because at the end of the day, these terms in the Hamiltonian that I mentioned depend on these details.
Great. Elsa, did you have another question?
Yes, thank you. So very nice talk, Roman. I wanted to ask you in the first part of your talk, what kind exactly of disorder are you introducing in your simulation? So what is the disorder that you consider is important? You just said that there is no much disorder at the interface between the aluminum and the indium arsenide. We also know that some disorder in the superconductor is also good to improve the proximity effect. So exactly what kind of disorder are you referring to?
Yeah, so you're referring to half shell, sort of as part of
Yes,
the
yes,
story.
to the first part of this protocol to distinguish with the three terminal devices the presence of true and not true Majoranas.
Yeah, good question. So, you know, and that's basically an important question that we need to answer as a community. What is the dominant source of disorder in these devices? I mean, first of all, it depends on device, but I would say I will give you the list of kind of my top list of disorder sources. So on the top of my mind is disorder that comes from dielectric. You know, we know that dielectrics have charge disorder. We have these dielectrics very close to the active region, and these charge impurities, they introduce inhomogeneous potential and they introduce scattering. So that's one source of disorder. And this is what I alluded to when I said that full shell wires are covered by superconductors. So in principle, you know, it's an interesting alternative system that does not have the source, and would be great to compare, say, you know, take full shell wire, edge half of it, and then compare how things start to degrade as you do that. I mean, of course, there are crystal defects and things in the wire itself. As we are growing these wires, there are defects in the wires. So the question is, okay, what's the scattering time introduced by these intrinsic defects? And I guess it depends on, you know, which specific wire we're talking about. You know, the indium arsenide, indium antimonide, and so on. There's interfacial disorder. So at zero magnetic field, things look good, better than in you know, original the indium antimonide, niobium titanium nitride work, but it doesn't mean that it's good enough, because as you can see, mean free, you know, localization length in these wires has to be pretty long, and these are quasi one-dimensional systems. So small disorder is going to introduce backscattering and is going to induce localization. So question is, okay, for are the interfaces good enough? Are they clean enough, and so on? So these are three top suspects, I would say. So
in your opinion, in the wires with partial cells, do you think the semiconductor community is going to be able to get rid of these sources of disorder soon? I mean, I thought these were very fine and clean already samples with very good growers. So do you think, is it possible to really reduce the disorder enough in the coming years?
Well, but this charge disorder is not introduced by growth. It's introduced by fab. It's how you deposit dielectric on top. And you know, if you want to talk about indium antimonide, which is low band gap semiconductor, the optimal condition for depositing dielectric are usually very high temperature. So you have temperature budget to work with, and therefore dielectrics that, you know, one usually uses in these devices is not of optimal quality. There are oxygen vacancies and so on. So it's not my domain of expertise. We should talk to some fabbers and you know people who are really experts on this topic. But that's what I think is the dominant source of disorder. It's not maybe the wire itself, but it's what you do with these wires afterwards.
Thank you. Thank you.
I think we really have to move on, but we can discuss this more. We have a discussion session right after the next talk. So thank you again, Roman, for this wonderful talk.
Okay, thank you.